Welcome back, everyone. Let's do part two of Scott's vendetta against the parking ticket writers in Sacramento. This time, it's a different design to the study. So we're going to talk about paired samples t-test. So the chief of the parking ticket patrol for the city of Sacramento, still a sadist, he's curious about whether the daily application of random electric shocks to ticket writers would increase the number of tickets that they write in a week. To control pre-existing differences among the ticket writers and their ticket writing ability, the head of the parking ticket patrol wanted to match the ticket writers based on their previous ticket writing performance. To do this, 24 ticket writers were ranked from highest to lowest by the number of tickets each wrote during the prior week. Then one of the top two was randomly assigned to wear an armband that delivers random electric shocks during the workday, and the other of the top two was assigned to wear an armband that does not deliver electric shocks. To continue down the list, this continued down the list of ticket writers in pairs so that the groups would be equally matched on prior ticket writing ability. Given that the 24 ticket writers were matched and randomly assigned in pairs to one of the two shock groups, that is X1 shocked and X2 is not shocked, this study has a within subjects design. At the end of the week, total number of tickets written by the 24 ticket writers is calculated as shown in the table below by armband group. It's in a data file, blah, blah, blah. The goal of this analysis is to test the following research hypothesis. And did the mean number of tickets written increase for the shocked ticket writers compared to the not shocked ticket writers? So it's the same data, folks, but this time the design is different. Here they've been matched based on their prior ticket writing abilities in pairs, and one was randomly assigned to get shocked or not. And so that is to equalize them on their ticket writing ability. The hypothesis is also different, right? It's not did they differ like it was last for independent samples T. Here it is that the shocked ticket writers will write more tickets. It will increase the tickets that they wrote. So, with that in mind, let's scooch on down. Is this research hypothesis above two-tailed or one-tailed? It's now one-tailed, right? It's one-tailed because there's a group that's being picked as the higher or lower one here. In fact, it's those who are shocked will write more ticket writers. So we got to write the hypotheses. So one-tailed, where they think X1 will be higher or X1 will be lower. This is where X1 will be higher. This is what we got to do because X1 was shock ticket writers. So our null hypothesis is that, let's start with the alternative. The alternative hypothesis is that those in group X1 will have a higher mean tickets than those in X2, so greater than. What are all the other possibilities where we would be wrong? Well, one of those is if they wrote fewer tickets in group one than group two on average. So that's part of the null. We'd also be wrong if there's just no difference. That's why the equals is in the null. So the null is less than or equal to. All right, let's check the normality assumption. So this time we are going to go and use the descriptives procedure. Why? Well, there are different variables for the tickets written for the two groups. So we can use frequencies, we can use descriptives. I tell you guys to use descriptives this time. Cool, so let's do it. So analyze descriptive statistics, descriptives, and put both these over there. Under options, make sure you get skewness. And do I tell you to get anything else? Nope. So continue and click OK. This gives us our shock ticket writers, not shock ticket writers. Way over here, we get our skewness statistics. You'll notice that, well, first of all, for shock ticket writers is negative 2.246. For the not shock ticket writers, skewness is 0.283. Are either of these things bigger than an absolute value of 2? Or do either of these have an absolute value that's bigger or 2 or bigger? The answer is no. So we have met the assumption of normality. So do the data appear to meet the normality assumption? That is the absolute value of the skewness statistic less than 2 for both groups? Yes, that's our answer. So now we're going to go ahead and run the actual paired samples t-test. That's under Analyze, compare means and proportions, paired samples t-test. It's set up a little differently here than independent, right? You have to actually pick and pair up the groups. So we want to compare shock ticket writers, and I guess there's two ways to do this. You can click them over to not shock ticket writers. You can click them over. Pair one is shocked and not shocked. That's one way to do this. What I do is I click one group, I hold down Shift, click the other group, and throw them over at the same time. It's just easier to do lots of them that way, and I do lots of these. So under options, nothing good. All we got to do is click OK. And let me scooch this over so we can actually see things. All right, scooting on down. What is the mean and standard deviations for the two groups? First table here, paired sample statistics, 158.42 for shock ticket writers, standard deviations 25.02. Not shock ticket writers, 128.25, standard deviation of 23.58. So using the alpha 0.05, do the data appear to meet the dependence assumption? That is there a significant correlation between the groups? That is paired samples correlations. We scooch on over here. There's our actual correlation coefficient, negative 0.091. It's not particularly big. We have a two-tailed hypothesis for this because it's just the assumption is just that there's some correlation between them. There is our significance. Is that less than 0.05? No, there actually isn't a strong correlation between the tickets written by these two groups. So we actually do not meet this assumption. So the answer is no. So do we give up? No, it just means that when you don't meet this assumption, you don't gain any additional power from doing paired samples versus independent samples. So let's look at our decision rules. For a one-tailed hypothesis, there are two requirements. The significance one-sided has to be less than 0.05, and the sample means have to differ in the direction hypothesized. That is, shock ticket writers wrote more. So first of all, let's scooch on over in our paired t-test table to our sig. One-sided, 0.007, that is definitely less than 0.05. So there is a significant difference between the mean tickets written by our groups. So part one is there a significant difference between them? The answer is yes, because sig one-sided is less than 0.05. So can we fully reject the null hypothesis? So second part here is the sample means do they sample means differ in the hypothesized direction? And we said shock ticket writers would be higher than not shocked. There's the two means. Shocked is higher, so yes. This is consistent with the parking ticket person's hypothesis that shocking ticket writers would increase the number of tickets they wrote. On average, about 30 higher. So why or why not? Significance one-tailed is less than 0.05, and the difference is in the correct direction. Shock ticket writers wrote more on average. Mean difference, two ways to get it. Again, you can just subtract these if you want, or down here where it says mean, that is the mean difference, 30.17 when you round it. Which group had the highest mean? Shock ticket writers. So shock ticket writers. We have to calculate omega squared again. Note the formula here is different. So we got to calculate it differently. And again, this is where the none of the effect sizes that give you are the one that you need. So we actually got to calculate this sucker. So I will bring up our calculator. Part one is t squared minus 1. Let's find our t value. There it is, 2.91. 0.91. We got to square it. We get 8.4681. We have to subtract 1 from that, so minus 1. Top of this is 7.4681. All right, that is the top of this equation. The bottom is t squared again, so let's go with 2.91 squared. And then we add degrees of freedom, where degrees of freedom is equal to the number of pairs minus 1. There's our n. There's 12 pairs in here, right? There's 24 total ticket writers. They were paired into 12 groups. 12 minus 1 is 11. So n minus 1 is 11. That's our degrees of freedom. So we have to add 11 to our t squared up here. So plus 11, we get 19.4681 in the bottom. That is that. So again, up top we have 7.4681. We divide that by the denominator, which is 19.4681, and we get 0.38 after rounding. So the answer is 0.38. 38% of the variability in tickets written could be accounted for by whether or not the ticket writer was shocked. All right, so we got to fill in our T's information using this little guide right here. We have a T with, we need degrees of freedom in parentheses, which is number of pairs minus 1. So 12 minus 1 is 11, is equal to 2.91, our T value. Our P was less than 0.05 because sig was less than 0.05, and our omega squared that we just calculated is 0.38. So interpret the results. What's the meaning? What do you tell grandma? You wouldn't just tell grandma, yeah, the ticket's written if they got shocked. We want to tell grandma how they differed. So what we would say is something like the shocked ticket writers wrote more tickets on average than the not shocked ticket writers. If you want to make it even better, say how much on average. So the shocked ticket writers wrote about 30.17 more tickets on average than the not shocked ticket writers. So does our interpretation above differ from the independent samples t-test from the prior week? I say no. We still conclude that shocking ticket writers increases their numbers of tickets written. Over the years, some people have said, well, it's different because omega squared is different. So technically, sure. I tried to reword this so it was more obvious. Does your interpretation above differ from the independent samples t-test interpretation last week? I think not. Interpretation's the same. They wrote 30.17 more tickets on average. So indeed, no. What is our backup test? So if we violate different assumptions, if we violate assumptions, what test can we use instead for paired samples t-test? To answer that, we need to go to the matrix of significant statistical tests. We find paired samples t-test in the bottom row. Look at the row above it. That is your answer. That is your non-parametric equivalent. And it is Wilcox and match pair signed rank test. And so the answer is that big old long name, Wilcox and match pairs signed rank tests. So that's it. So go ahead and use the template to do your APA write-up, and hopefully this was helpful.